Sorry, I just put the recording on, so I might as well answer that question. The question was about 3D textures, whether or not they're complex to use. Not really, but there are a few steps to it. You have to read in the file somehow, like the texture file itself. You take the image and you set it into the memory of the graphics card, and you just have to make sure how you're kind of sampling the location within the texture and setting that to each vertex. We'll cover it nicely, how you texture map and how it works. So it shouldn't be too complex to use after you kind of learn it, but looking at it for the first time, it's a few places where you have to change your code and a few things that have to go correctly. So it can be a little bit complex first time. So today's lecture is going to be mainly on three-dimensional meshes, three-dimensional models, kind of how we set up polygons and vertices and normals for three-dimensional meshes, how we store them, or possibilities of storing them as a file and optimizing the way we send them through OpenGL, kind of different ways than the Vertex Array that we've been looking at now. Nothing very different, but kind of a way to structurize our three-dimensional meshes and models. Before I start that, I'm going to I'm kind of going to correct the thing I did incorrectly or forgot in a lecture here and that affected your the outcome of your hand-in assignments a little bit, and I'll fix that. I'll just explain a little bit what I did wrong and what it looked like. And in the end, after we talk about meshes, I want to cover a little nice algorithm to kind of automatically generate mazes. It's not something that's a requirement in the assignment that you're doing now, but it's something that's fun to do, and it's a fairly simple algorithm, and it's both to show you that algorithm and also just to show you kind of ways to think about the maze in this assignment and think about the three-dimensional environment that you're setting up. So, first things first. When we're talking about perspective projections and mainly setting up a camera in a specific location here where we have basically the main z-axis or the n vector backwards here, we have y-coordinates here, we're looking with the camera like this, so basically the set perspective function. We know how we set up the projection matrix using near, far, left, right, bottom, and top, but the way we calculate near, far, left, right, bottom, and top from an angle here, or the field of view, and basically the near plane, also far plane, but that's less important in this correction here. So we have the field of view, we have the aspect ratio. Everyone was using this correctly. The thing that I did wrong in the last lecture is simply I forgot when I set up the formula here for top equals something, 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 tangent of the field of view divided by 2. This would be correct if this were a unit circle. So if I have a unit circle, it's 1 here, then this y-coordinate here, which would be top, would be the tangent. However, since this is the near plane, it's not always 1 and can be anything we want it to be. This would be a circle with the radius n. That means our top coordinate will have to be the tangent multiplied by n. So this was in the slides that were online, this was in kind of material that I put online, but when I did it on the whiteboard in my lecture, I simply forgot to take the n and multiply it here. I know some people used that as kind of a template for their assignments. I'll correct that. I could say that, you know, you did it wrong anyway and, you know, should have understood how this was blah, 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 but it's not the grade in the end that matters, but just to understand why something was wrong that you did and correct it and do it correct from then on, or just learning the material through doing the assignments. So if I don't correct this in the next few days, you know, just send me an email and let me know that this was exactly what I deducted points from your grade for. So no big deal, but the idea here is, yes, we are at the near plane, so it's not enough to just take the tangent, which would be this height here and set it to top, we actually have to make sure that the circle we're working at, the distance from the center that we're working at is n. So we also have to take this height here being n times the tangent of our angle heft. So that's my correction. I hope it'll show nicely on the video as well. And you can pause it exactly where we were a moment earlier. I hope we don't have a lag in the video exactly before I set this up and then suddenly I've erased everything when the image pops back in. I'm hoping my network connection is better now anyway. All right, so let's just start on this side of the board. So I hope I can keep this fairly short because this is not kind of complicated material. It's kind of taking a lot of things that we've already done and kind of adding them up into the way we store or define models or meshes in 3 dimensions. So we've already looked at the idea that we have the model view matrix and view matrix where we kind of take entire models and we transform them through space into other locations. So what we're doing now is basically defining ways to store the models kind of in their own world with their own kind of little center of the universe within themselves that we can then draw in different locations in our scene. So if you just imagine something like, well, simplest thing here would just be our cube that we've already done. Let's imagine them drawing it from the corner rather than from the center, and it becomes even simpler. So we have, trying to see exactly how this is gonna. So that. Something like this, and then we have these sides inside. All right, so we have this cube here. I'm gonna put the blinds down so that we don't have such reflections. Yes, thank you. Lights. Okay, so if we look at this cube and we want to be able to send this into OpenGL and tell OpenGL, I want you to draw this cube. I want you to draw it so each of these sides is filled in so that it looks like a solid enclosed 3-dimensional object. What information do I have to send into the OpenGL pipeline for this to happen? Like, what are the base things that this cube needs to have? What's the first thing that I can fairly easily? Sorry? Vertices. Okay, vertices. So I need vertices. For each vertex I need a position. So I have these 8 vertices here, which are basically the corners of my object. So in this case, I have a vertex that's 0, 0, 0. Just set up a list of them here. So position or vertex. So I can just set up a list of vertices here. I have a vertex that's 0, 0, 0. Say 1, 0, 0. 0, 1, 0, 0. 1, 0, 1. 0, 0, 1. And then I have all those same except here on the top, which means I can draw all of them again, except with the y coordinate. 1, 1, 0, 1, 1, 1, and 0, 1, 1. Okay, these are all the corners of this cube here. So if I send this into OpenGL, like, what else do I have to do? In the programs that we've looked at, then we don't have just 8 vertices in a list, right? What do we have? Like 4 times 6 is 24. 24 different vertices that we send in for the cube. Because we kind of repeat all of them for each face here. So the vertex array that we send in, we say, I'm going to draw this vertex, this, and this. Then I'm going to draw this one, this one, this one, and this one. And this one, this one, this one, and this one. And we see that this vertex here, I've now repeated it 3 times. Because each vertex is part of 3 faces here. So that's the way we do it now. We just set up a vertex array that not only holds all the vertices, but every single time that vertex is drawn as part of a polygon. So in that case, it'd be 8 times 3, so we end up with 24. Or we can say we're drawing 6 faces, and each of these faces has 4 corners. So it's 24 vertices that we're sending in there. And that's because we're reusing them a little bit, because we're drawing each face as 2 triangles. But when we send it in, we draw it as a triangle strip rather than triangle fan. Either way, we send the vertices in, this vertex, this vertex, this vertex, and then we kind of reuse 2 of them and draw the second triangle. If we were to send all the triangles in, each one of them, it would actually be 12 triangles with 3 vertices each, which would make it 36 items in our vertex list. But we want to be able to set this up, so we just repeat these vertices, well, once. At least in the best possible case, we're going to look at it that way. So in order to do that, we need to look at polygon here, polygons. So we're going to say we have positions, and then we have polygons. And each polygon would say, usually we're just using triangles, but let's say we have kind of a number of faces on them. We're going to say this polygon has a number of vertices in each polygon. It has 4 vertices. And then I'm simply going to look at this as an index here. Index. Let's say this is index 0, 1, 2, 3, 4, 5, 6, 7. And I'm going to say the first polygon here. So if we skip this, can we mark the indices in here? This would be 0. And we said 1, 0, 0. This is the next one. This is the next one, and this is the next one. Then we go up. So this is 4, 5, 6, and 7. So I can say the first polygon I'm going to draw. Let's say I'm going to draw the front here. I'm going to draw the vertices in this order. I'm going to draw vertex number 3, vertex number 7, vertex number 6, and vertex number 2. So that's my first polygon. That's the front face. Next polygon. So I'm drawing these now in a way that if I'm looking at the front face of the polygon, I'm defining the vertices in clockwise order. And that's something that can actually make a difference with some of the algorithms that OpenGL has. Culling, and things like that, where you actually calculate the normal in a specific direction, and it matters if you're looking at a front side or a back side. You can also, in some cases, color polygons differently on the front side and on the back side, or even light them both on the front side and the back side. So flip the normal if you're looking at the back side, but use the original normal on the front side. In many cases, we don't use any of this, so it sometimes doesn't matter if we do this, but it's nice to keep in mind that the best way to kind of define these the vertices in a polygon is to do it in a clockwise order when you're looking at the front face of the polygon. So if you take the back face now, That would be 1, 0, 4, 5. No, because we're looking from the other side, it would be counterclockwise there. So this one was 3, 7, 6, 2. This one here would then be 0, 1, 5, 4. 0, 1, 5, 4. So the top face here, 7, 4, 5, 6. 7, 4, 5, 6. So on and so forth. So is there something that we're lacking kind of here? We have the positions now, but since we've looked at the ways we light this, right now we're not getting any information on how we want to light these. We could say, well, I just have to make sure that all the normals are calculated as soon as I'm sending them through or as soon as I'm getting them from the file. And in some cases this is done. In some cases we just have the positions and the polygon set up, and then simply policies of how the normals should be calculated. Should they be calculated smooth? Should they be calculated kind of one polygon for each face, no, one normal for each face, or one normal for each vertex as some kind of weighted average of the adjoining polygons and so on and so forth. But it's also nice to say, to explicitly define the normals. So that's another thing we need. We have the vertices themselves. The other thing we need is to say, for each of these faces, we also have, I'll draw in a different color here. We also have data that tells us in which direction each of these vertices is facing. So this one is facing here forward. This one up here is facing directly up. This one on the back is facing directly backwards. This one on the side here, facing to the side. So here facing to the other side. One at the bottom here, facing down. That's all of them, I guess. So these normals also need some data. So we can say this normal here, what are its coordinates? This one is 1, 0, 0. This one here is 0, 1, 0. This one here is minus 1, 0, 0. So on and so forth. So we have vectors that tell us in which direction each of these polygons or each of these faces is facing. And we want to have normals as well. All right, so we have the vertices here. In this case, I'm going to set up a separate list for the normals. Then we're going to talk a little bit about how do we kind of send these normals and positions through the OpenGL pipeline. And in the programmable pipeline, in the end, we're always sending parallel lists. So in the end, we need to have lists that are set up in a way where a vertex or a position and its corresponding normal are in the same index of these lists. So we're using the same kind of indices to locate both of them. However, in this case, I'm going to make it as general as possible. And I'm going to say we can actually set the normals up independently. I'm going to say the normals that I have are 1, 0, 0, minus 1, 0, 0, 0, 1, 0, yeah, 0, minus 1, 0, 0, 0, 1, and 0, 0, minus 1. So I just set up an independent list here, and we have an index there as well, 0, 1, 2, 3, 4, 5. So we have one index for positions, one index for normals. So in that case, we also have to add a little bit to our polygon, so I'm going to make this a little bit tighter here. And say our first polygon here had 4 vertices, and the indexes for these 4 vertices in the position list are 3, 7, 6, 2. And for the normal list, this front face here has the normal 0, 0, 1. That'll be this one here, which is 4. And we just say 4, 4, 4, 4 in this case. If we want to make it absolutely general, where we can have the same or different polygons, we could also say, if this is kind of flat surfaces anyway, I could say all of these just have the same normal, and just have one normal here. We could define this more general and say, some polygons just have one normal, and then we set the same normal to all of them. Some of them have different normals per vertex. Well, for now, let's just say we're sending it in like this. The next one was the back face. There we had 0, 1, 5, 4. 0, 1, 5, 4. Those are our indices into the position vertex list. And it's right on the back, so it's this one, 5, 5, 5, 5. The next one that we did was top right, where we had 7, 4, 5, 6. And that one has this normal here, the directly up normal, which would be 2. And then we could make these types of lines for every single one of these faces. And so the question is, once we've set this up, once we've set up this kind of file or this structure, if we want to set up a program that draws this, like what is the entry point for this program into this structure in order to draw this? Like which list does it look at first? Like if we look at the polygon list, that's a list of a bunch of indices, and all of these indices here are indexing into these lists. So this is kind of our entry point. We say, I want to draw all these polygons, because polygons are kind of the units that go together through the OpenGL pipeline. Yes, vertices we send individually through the vertex shader, but at some point we want to take these vertices together as polygons. So those are kind of the units that we need to send in. So here we have them grouped as polygons. So our algorithm for drawing this would be, I'm going to go to the first entry in the polygon list, and maybe it's more detailed, maybe it says these are 4 polygons and they're supposed to be drawn as a triangle strip or supposed to be drawn as a triangle fan. Maybe there are more and we draw everything as kind of a triangle fan and just go counterclockwise or clockwise around the polygon itself. Either way, we go in here, we get this policy, and then we can simply say, all right, I know what I'm going to draw, or I know how I'm going to draw this. And once I've said that, I know that I'm going to send first this polygon here, number 3. Oh no, sorry, this vertex, this position. So position number 3, I send through the vertex shader. Once that's done in the vertex shader, I send position number 7 through the vertex shader. I send position number 6 through the vertex shader. Position number 2 through the vertex shader, and then they're grouped together, and I send them through the rest of the pipeline together. Except I have to make sure that I take position number 3 along with the normal in index number 4. So this vertex and this normal. Because in our vertex shader we have attribute variables. In our current vertex shaders we have attribute variables for position, and we have attribute variables for normal. So those are the 2 attribute variables we have. So we need to make sure that we take this here position and this here normal, and we send them together through the vertex shader. Next we take position number 7 and again normal number 4. We send those together through the vertex shader and get the values corresponding to that. Then position number 6, so these values for position, these values for normal, send them through the vertex shader. Once we finish one of these, then our algorithm will simply say, okay, now I'm going to draw the next polygon here. And I'm going to do all that same thing. I'm going to draw the next polygon, and so on and so forth. So this is basically a way to set up a more complicated model, because the box is simple. We can just hard code the points. Or the sphere, if you look at that in the last kind of programming video. I didn't do it live, but I had done it, and you can look at the code for the sphere. It's basically these double for loops that just go in a very systematical way around the surface of a globe and build a vertex array with all of these positions based on the cosine and sine of different angles. But it's very systematic, and we just kind of go mathematically around the globe. So that's simple enough when we have these very standard forms. But as soon as you have something more complex, like, you know, you have a house here, we set that up here in our coordinate system, or, you know, even more complex, we have a modeled image of a face or of a head. You know, we have these really complex models, and we can't just calculate them mathematically from base objects. Then instead we need to set up these vertex lists. So when we build this structure, it's simplest to start with the positions. We can kind of take all the positions along the surface of this complex object that we have and set them up. We can either calculate the normals in a program by taking all the adjoining positions and seeing, okay, if this is a triangle, then I can calculate the normals for that using cross products or something similar. And we can build the list of normals, and once we do that, we kind of take all these polygons that enclose this area of this model that we're drawing, and we set up, okay, this polygon is using these three vertices and these three normals, and then we kind of set up this list. So in the end, the polygon list is a list of all the polygons that is enclosed this complex object. Are there questions regarding this? Or does this feel like natural and I'm not going to say simple, but just, does it feel like something that makes sense? So this is kind of our base way of setting this up. If you want to look at it a little bit more in terms of OpenGL, let's switch here. What we have used at this point to send polygons through the OpenGL pipeline is we've basically set up arrays. We've set up a position buffer, and then we just set up a bunch of positions, and we set up a normal buffer, and we have a bunch of normals. And in our case, we did something like, just for the front face, we had 0. Start there. 0, 0, 1. We have 0, 1, 1. If we go around, we have 1, 1, 1, and we have 1, 0, 1. So that's just the front face. If we now go to the side, we're going to do 1, 0, 1. So this one is repeated. 1, 0, 1, 1, 1, 1. Again, this one repeated again. Go back to 1, 1, 0, and 1, 0, 0. All right, so now we've just done kind of two polygons here. First polygon and the second polygon. Now the normal buffer would need to make sure, because we read them always, if we're reading from index 0 in the position buffer, we're also reading from index 0 in the normal buffer. And we're going to keep on doing that throughout, even though we can optimize this a little bit, can't completely lose that. So for the normal, the front face is 0, 0, 1. So we're doing 0, 0, 1, 0, 0, 1, 0, 0, 1, 0, 1. and face to that side is 1, 0, 0, 1, 0, 0. All right, so the question now is, what we do at this point, okay, is when we draw this, we call GL draw arrays. And that takes something like GL triangle fan, and it takes a number, which tells us where we want to start. So for the first polygon, we'd start at 0, and we're going to draw 4 vertices. And then we call GL draw arrays again. The same stuff, except this time we're going to start at index 4, and we're going to draw 4 polygons. So another thing that we can do, and actually when we look at this for the cube itself, because it has these flat shadings, there's not a lot of optimization in the amount of data in these that we can do, because we actually need to have pairs of these lining up. But another function that we can use in OpenGL is the function GL draw elements. And what GL draw elements does is that we start by telling it what we want to draw. Let's say we just do GL triangles. After triangles, we tell it how many we want to draw. So let's just say we're going to draw 4 triangles here. Triangles. Or actually, before that, there was type, which tells us we want to draw 4 triangles. GL, let's just say in this case GL short. And then we have basically an index array. Index array, let's call it index list. So our index list, in this case, index list would be a list basically of indices that tell us in which order we want to draw this. So if I'm doing triangles here, in order to get the same thing, I'd like to draw first this triangle and then this one, went around. Okay. So I'd say for the first one, I'd say index number 0, 1, 2, then 0, 2, 3, then 3, 4, 5, 6 for this one, and this one, which is half of the next face, and then this one, and this one. 4, 5, 6, 4, 6, 7. So I do this first, then this. So in this case, even though it doesn't help us very much when we're drawing this very simple object, it doesn't really optimize much for us here. It's simpler to show you how it works with a simple object, and then we just have to kind of relate to how this would optimize a more complex object. So here I'm simply setting up an index list, and this index list, where all of these would be in this case short, it could be GL, I think it's GL int, GL float, there are a lot of types in OpenGL. So it's just an index list, and short is usually enough unless we have an index list that's bigger than, I think, 20-something thousand. So what we send into OpenGL is we make sure that OpenGL has these vertex lists already down in its hardware. We make sure that we've already sent this to OpenGL. Then the only thing we need to send to OpenGL in order to draw this is just the index list. Are there questions regarding this, or something that you find unclear in this idea? So while GL draw arrays simply goes to a specific index in our vertex buffers and draws a certain amount. And we can index into a certain place, and then it just draws linearly from there. In this case, especially if we have more complex objects, we have a object that's built up of a bunch of different polygons here. Some of them may be really weird structured, things like around the nose or around the eyes or something in a face model. It can be super complex like that. Then we can say I have all these vertices and their corresponding normals, and then I just set up an index list where I just send the indices. So this polygon here would be 0, 1, 2, this one would be 2, 1, 3, this one would be 2, 3, 4, this one would be 4, 3, 5, 3, 6, 5, 3, 1, 6, 1, 7, 6, so on and so forth. So we're just sending indices into our model rather than kind of indexing into this list and just going linearly from here. You can see in a complex model like this how much we can simplify by sending all of this in as a list rather than having to send every one of them linearly as they are and then repeat them accordingly.
How do you handle the normal vector in this case?
In this case?
Yes.
So now this is one of these places where kind of a lot of explanations build on explaining other things and then I'm going to explain later. So let's just take that now then. There's another idea in these models that make things like the cube that we were looking at, something that has these specific normals for each face. So all the vertices in this face have this normal, and all the vertices in this face have this normal. So handling these normals actually means I need to duplicate some of the data, because this vertex, this position here with this normal, is not the same through the vertex shader as this one. And since when we're sending into the vertex shader, we need to read the same index from both of these lists, just because of optimization and how we deal with this. We actually need kind of two places, two duplicates of the same position because it has a different normal, which means the entire vertex data here is not the same. However, if I take something like a sphere, I'm just going to look at it in 2D here like a circle, and we're going to say the model for the sphere is not really a sphere, it's more like a big, kind of in this case for a circle, like a big polygon. In the sphere, we just take that to 3 dimensions. And what we want to do as well is that if we were to say this polygon has this normal, and this polygon has this normal, then the lighting would be such that when we draw this vertex here with this normal, we're going to get a different result from the vertex shader, right? Than when we draw this vertex with this normal. So these are different values, which means we're going to get a different color result from the vertex shader, which means when we look on our sphere here and we see two adjoining polygons, one of them is going to be darker than the other in its entirety, and we're going to see it like in a line here, like looking at a tessellated sphere, something that's not an actual sphere, but like looking at the pearl, with its windows. But what we want to do is we want to actually get a smooth surface. So in that case, we actually say I'm not going to define a vertex nor a normal for each polygon, so that this vertex, when it's drawn as part of this polygon, it has this normal, and this vertex, when it's drawn as part of this, it has this normal, and then these have this normal. Instead, I'm going to say I'm going to define one normal for each position. So my vertex is a normal and a position, and for every single polygon that uses that, I'm going to use the same kind of full vertex with the same position and the same normal. What will happen here is that if we draw these two polygons here, we're going to get some value for color here and here. We're going to get some value for color here and here. When we draw this vertex as part of this polygon, we're going to get the same value from the vertex shader as when we draw this vertex as part of this polygon. Does that make sense? Because we're using the same normal. We're not using a normal that's exactly perpendicular to this face and then to this face. We're using some kind of average between them. And we're going to say we're going to use that normal for both of them. This means that on this line, we get exactly the same value when we're calculating for this polygon as we do for this polygon. And after that, shading is what happens, and fragment operations. And we haven't gone much into those, but the result will be that we kind of get a gradient from this color here over to the color of the values that we got here. And on this side, we're going to get the same values here and then gradient to the values on this side. And then for the polygon that kind of meets this one here, again, we have a normal here, and those normals are used for both of these on these sides, meaning that we're going to get a smooth shading over the entirety of it. And getting back to this here, if this is shaded smoothly, which most three-dimensional models are, well, most kind of three-dimensional game models and such, usually most of the surfaces are smoothly shaded. This kind of not really solves two problems for us, but it makes two things nicer. Number one, it makes it look nicer, because if this is, let's say this is some kind of face model here, we have kind of eyebrows here, we have some polygons defining the bottom sides of the eyes here, something defining kind of a nose here. I know I'm not very good at drawing this, but you get the idea. You know, this is a face, we have all these different polygons, and around detailed things like the nose and around the eyes, we have a lot of polygons. Over something big like the forehead, we can have fewer polygons. You know, so we end up with this. We have a mouth here and very, very detailed, and kind of cheekbones here, so on and so forth. So we have all this detail, but we don't want it to look all boxy. We want it to look smooth, like a smooth transition over all of these polygons. So each of these vertices that define this, we're going to give its own normal. So each vertex has its normal, and then we build a vertex list of that, where all of the vertices have their own normal. And that means we don't need any duplicates, because if the same position is part of, like this one, part of 1, 2, 3, 4, 5, 6 different polygons, it still has the same normal in all cases. So we've reduced our vertex list down to just one per position, because each position has its own normal. So it's not a normal per face, per position, it's just a normal per position. So that's the first thing we get. We get a reduction in the size of our normal list, and we also get the nice kind of smoothly shaded effect on this. Basically smooth shading, the gradient over everything. And it's easier to look at this in a program. We'll do that, you know, in due time. Look at how the difference between shading something smoothly and shading something flat looks, number one. And we can also look at how many more polygons we actually need to shade something flat than we need to shade it smoothly. Do you have another question regarding that, or did I answer?
You answered the question, I think it's going to follow.
Okay. So I answered the follow-up as well. Fair enough. Okay, so this seems complex when we're kind of looking at it for the first time, but in the end, what we want to do here is we want to be able to shade things smoothly, and we want to be able to define one normal for every position. This also reduces the size of the list. So if we need to draw something like a cube, sadly we have to say the combination of a position and a normal is one vertex. So this position here with this normal is one vertex, this position here with this normal is another vertex, and this position here with this normal, kind of out the back, is a third vertex. So we actually need 3 entries in our vertex list for the same position, depending on what normal goes along with it. However, when we're shading something smoothly, like we take a sphere. So if you just take a regular sphere, And you can actually look at this in the code that I put in one of the videos. For instance, if we take this vertex here, this vertex here is kind of calculated as a vector from the center of the circle. If you draw this again as a circle, the position, if we imagine that this is a radius 1 sphere, the position is just basically the value of some unit vector there. The translation from the center to the surface at this particular point. And we get some x, y, z here. The normal to that particular place, if we take this outside here, say, okay, this is the radius, or the radius 1. The normal to this position has exactly the same values as the position, right? Because the position is a location on the surface of a unit sphere, so it's a unit length. If we just take those same dimensions, or those same coordinates as give us this point, when this here is the center 0, 0, 0, those same coordinates will give us a vector that points directly away from the center of the sphere in that same direction. So when we're building a sphere, we can actually use the same coordinates for the position on the surface of the sphere as for the normal. And in that case, if we're going to smoothly shade it, we can simply set these up, kind of these unit vectors with a cosine of some angle and the sine of some angle, up in both the position and normal buffer alongside each other. And then we can read through those in a specific order. Are there further questions on this? Now, when these models become more complicated, we need kind of more complicated ways, or more, let's say, more data for all of this. So something like this is in the end going to be set up basically as these kind of chunks of data in a model. And it'll say, okay, I have vertex lists that have specific IDs. So maybe a model is comprised of several kind of model parts. And then we need to set up this huge vertex list and a huge normal list. And then each of these parts will have an ID. So in our file, we set this up as a file. We can have something like a position list. We can have a chunk here that's the normals. Then we might have a chunk here that is different materials. So where we would define different sets of diffuse color, specular color, shininess, maybe a texture, maybe texture coordinates, things like that. So we have different materials. And then in the end, and position and normal, if we're going to line them up as part of each vertex, then actually position and normal could be interleaved instead. So it's position, normal, position, normal. This just depends on what the file structure is in each case. Then in the end, we'd have basically model parts. And each model part, we just kind of size that up here, a model part, and that would have some material ID. So the materials would be in a list, and they had an index. So we had an index list of materials. So we'd have some material ID here, let's say the first material in the list. Then we'd have something like vertex list, and that would then just be this list of IDs. I say, okay, I have a polygon that's 0, 1, 2, I have a polygon that's 3, 7, 6, I have a polygon that's 8, 1, 0, so on and so forth. So each model part would be this, and then I just have another model part. And that might have a different material, but it's still indexing into the same list of positions and normals. So a file structure would be something like this. And this would actually be a very simple file structure, because a lot of these will get more complicated by setting up texture coordinates into this as well, so on and so forth. During the either next session Monday or the week after that, I'd like to kind of look at some file structures, simple file structures that do this. The problem with this is that we can look at file structures that are set up as, for instance, XML or text-based file structures. And it's easier to read them and easier to understand them, and you can kind of read them with an XML loader and code and kind of see what's happening. But when it actually comes to loading them into our data, reading that amount of text is just, it takes an immense amount of time. So it's actually super slow to use something like that. We could instead use what's usually used, better optimized, which is some kind of binary file structure that just has these chunks of data where we have to know the exact kind of structure of the file, know how to read the file's header and what it says and how many vertices there are in the list and how many materials there are, such and such. It's more complex to kind of make sure that everything works, and if you have an error, it's more difficult to find it because you just don't have just this text-based file that you can read from. However, it's very, very, very much faster, like so much faster that it, this becomes in the end almost unusable when you have big models, because reading text files of that size, where every single polygon is actually rendered or kind of defined, or sorry, every single vertex is defined as actual numbers with commas between them, actual kind of not numbers but strings of text. Because a simple number that takes, let's say, 4 bytes in a program can end up in a text file being 0.0125. If we want this to be detailed, which it often is in small models, we need to be fairly exact. Then you can see the amount of bytes that we're going to end up using for every single number in this. So, yeah, and the XML structure, or not XML necessarily, JSON structure, something like that, something nicely readable, is good to work with to begin with to understand this, but can be very cumbersome to work with once you start getting it going. So I want to look at different structures, but I want to make sure we look at simple structures so we don't kind of get overboard in trying to read all kinds of different stuff that we don't need. So yeah, that's kind of what I'd like to do soon, probably after we hand in the assignment that we're working on now, to kind of look at model files and make sure that we can actually read more complex models into our programs to display them, rather than only working kind of with these very simple models like the sphere and the cube, which we can mathematically define. Questions regarding all of this? Does it make sense? Does it feel natural? I'm just wondering if there's something I'm forgetting. I'm not going to go into calculating normals specifically, but you can go, I'm going to open the window a little bit here. You can go to, well, on modules on Canvas, there is a kind of lecture video, slide lecture video on 3D meshes, where I go through more or less the same stuff as I've gone through here, but you can kind of look at the slides there and maybe things are better organized. But also in the end, it looks at ways to calculate normals for vertices, normals for polygons, both by finding 2 vectors in there and doing a cross product, and also ways that are both better optimized and with less chance of error, because of the thing with cross product when we're working in a program is if we're doing cross products of vectors of very different lengths, or just cross products of any vectors, the cross product itself will be of a very different length. These can give us kind of small, not errors, but inconsistencies and kind of floating point loss of detail. So there are some ways of calculating these, and ideas on, rather than defining them, we actually need ways to calculate the normals themselves before we send them into the file. Or if we read files where they don't explicitly define normals, but instead expect you to calculate them, then that's something you need to do. So in order to read a file like this, what we would do is we would take the position list and normal list, and we would read it into kind of structures of our own, right? If there is no normal list, then we would have to take the position list, and we'd have to go through kind of these vertex lists in the model part, and we'd need to take kind of each of these polygons that are defined, and we need to calculate the normals ourselves. This is fairly complex to do, so I'm going to try to look at file structures that actually explicitly define normals, and make sure that if we use something like blend, that we can actually explicitly define or make sure blend kind of saves the normals along with our data, rather than just expecting the program that reads it to calculate it itself. But anyway, we'd either calculate this or read it in, and then we'd have these big structures in our programs that have these. Then we'd take these vertex lists as well, and we'd read those in, and then we'd have our structure. When we then display it, we have to make sure that we tell OpenGL, these are the vertex lists that we're going to be reading from, and here's an index list that I want you to draw. Or if we have the materials as well, then set the corresponding uniform variables, set the material specularity, the material diffuse, the shininess, all of that from this material that we save. But in every case, we wouldn't be reading this from the file every time. That's more like a loading thing. We'd say in the beginning, when we open the program, we just take these files, we read them into memory, into our own structures, make sure they're structured in a way that we can send them into OpenGL. And then we would go through these vertex lists here and make sure that we can send this vertex list in its entirety into OpenGL, along with or having sent the vertex buffers themselves into our hardware. And then the only thing we need to send down is these indices, and it'll draw from its own memory from then on. I'm going to imagine I've covered this more or less. You should look at the slide lecture as well and see if there's something that I'm doing there that I missed here. But rather than take a break, I think it's okay if we just go a little bit through a simple algorithm here for automatically generating mazes, and then we'll just be done. Is that better than taking a break? Spending more time on that. Can I erase this? Is everybody cool with that? Is there anyone here who has already done an automatically generated maze? No? Anyone who's interested in doing that? Yes, cool. Everybody? So much fun to just be able to, rather than make a level file or kind of hard code every single wall so that you get a nice maze, to instead be able to just tell your program a certain size, and then it'll set up a maze, and it just works every time. Before we kind of look at that algorithm, we also have to decide kind of how are we defining kind of the cells in our maze. So again, setting up the maze in this way is not necessary in this project. You can set it up differently. You can simply set up different objects and walls with specific locations within your area, so that everything kind of has a free-form position. You can just say, okay, each of them has an actual position and an actual angle, so I'll put one here, put one here. You know, they can have different heights, different sizes, everything. But setting up a fun maze to walk through in this way can be super complex. So often it's nice to go ahead and say, I'm just going to set up my structure in a super structured way, like on a grid. And I'm just going to say, the only place a wall can be is on this grid. So I'm going to set it up in a way where I just have a wall or not a wall on each of these lines in a grid. What I like to do is to say, I'm going to have, it doesn't need to be a class specifically, but let's write it up like that. Have a class that's called cell, and the cell has a Boolean value that would be, let's say, south wall and west wall. So a Boolean value that is south wall, and a Boolean value that is west wall. And that's the only thing a cell needs. So what a cell can tell me, so my maze would basically be somewhere down here. I have maze that is basically, I'm not going to write correct Python code here. It's something like this, then for blah, 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 blah. Let's imagine it's a cell, and we have width, and we have height. So we have a two-dimensional list or two-dimensional array of cells. So every time my camera is somewhere, or my position is somewhere, number one, what I can do with this grid is I actually don't need to have complex calculations to figure out in which cell I am. I can simply index right here with my position. If we imagine that each of these cells has the width 1, then I can actually take my position and I can take the integer of the floating point positions of x and z, right? So I have x here, I have z here. Let's imagine we're doing it in the positive direction of z. So you can just drop the fraction and say the integer that I'm left with, if I just floor my x and z positions, that is an index into my maze, right? Or if this is not 1, but instead some cell width or cell size, I can do the exact same, except I take my position, I divide it by cell size, then I drop the fraction, and I have an index directly into my maze. So I know what grid I'm in. So sometimes I just want to, for instance, in collision, I just want to check, is there a wall here, is there a wall here, is there a wall here, is there a wall here? Then I can simply index into my position here, and I can look at the positions around it, or the cells around it. And in this case, I can say if I'm walking kind of in this direction, and I'm in this cell, it's easy for me to check, is there a west wall? Then there's a west wall here, and I have to collide with it. If there's not a west wall, I can walk through it. Is there a south wall? If I'm going this direction and I want to check, is there a north wall? I simply need to go to the next cell and ask, is there a south wall there? So that's the reason I only have south wall and west wall and not north and east, is because my north wall is cell number my x and my z plus 1 and a south wall. And if I want to check if there's an east wall, then I simply have to say, okay, my position x plus 1 and z, or my position x plus 1 and my position z are the indices into this cell, and I check if that has a west wall.
So,
Yes.
Top on the right side, do you have to have your cell size one bigger than you want it to be, so you can have one that you can actually go to the right and say this one has a west wall?
Okay, the question is, if this is my effective maze, do I actually need to add a dummy row and a dummy column? Yes, I would do it that way. I'd just add a dummy row and a dummy column. Or I would just add to my check, if if I know the width and the height, I just say, if my height, or like my position is equal to height, or equal to height minus 1, I'm not sure which. So I just have a double check. It's like first checking, or like if the position dot y has become height, that means I'm at the top. And then I just automatically decide that there is a north wall. Or something, 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 number x, z plus 1 dot south wall. get the idea right.
And
So one or the other. Either you would have a dummy row and a dummy column that you can never go into, or you just add, am I actually at the top level? So I'd say, am I in the highest row? Or if I'm not, is there a, so this kind of check would check this first. If it gives you true, it won't ever check this, so you won't index outside. Because it's an or, then as soon as it has one true, it'll just stop checking. So this or will make sure that you check this. If this is not true, you'll check this. So you never check this if you're too far. One or two, these are kind of implementation details, but yes. One possibility is dummy row and dummy column. Another possibility is just to add to the check if you're already at the highest row or the furthest column, then you don't want to check to the side, then you're just going to say, well, then there's always a wall. And you can do that in your display routine as well. You can say your display routine just always draws a wall there. It doesn't care what the cells say, it just always draws a wall outside. So one way or the other. I don't care which is done. So since I mentioned the display routine, so something like collision, we're actually indexing into here, we're just checking a few columns here. The display routine though, it's going to go through the whole thing every frame. Except if we optimize that and make sure we only go through what can be seen, that's a cool thing that you guys can do. But in that case, our display routine is kind of starting here, and then it's just going kind of in a double loop through the width, through the height, and checking, is this current location, does it have a west wall? If so, then I'll draw that. Does it have a south wall? If so, I'll draw that. Go to the next cell. Does it have a west wall? Draw that. Does it have a south wall? Draw that. Next. And we'll just walk through the whole thing. All right. So that's kind of my idea of a maze structure. And again, I emphasize, I'm not setting this idea up because I think it's a better idea than anything else. I just think this is nice. This is the way I think mazes. But you can set it up in any way, like free format, a different type of grids, you know, where walls are in cells rather than on the edges, so on and so forth. This, however, leaves us with this nice algorithm that I'm going to look at next. So if we take a maze like this, a maze structure, and we close every single wall. So we make sure every single wall is set. And we just actually go through the cells. We initialize the cells with both west wall and south wall true in every single cell. Now I'm going to close the window again because it's getting cold. And then you start somewhere. It doesn't matter where you start. You can actually start in the middle of this or at the end or wherever. I'm going to imagine that let's just start here. So the algorithm goes like this. The data that we need kind of a stack where we put different cells, or we put cells on this stack. Let's do it from the bottom here. Cell, cell, cell. So we have a stack of cells, and we start out empty. And another thing, every single cell that we have, we need to be able to mark it visited. So these are the only two things we need. We need a stack of cells, and we need to be able to mark cells as visited. Then we start somewhere. In the first cell that we start at, we mark it visited. And then we randomize. And this randomization actually has to take into account where I can actually go. So if I'm at the furthest column here, or whatever's left of me is already visited, then I can't go there. If I'm at the bottom, or whatever's below me is already visited, then I can't go there. So I count how many I actually can visit, and then I randomize a number, between 1 and that, right? So in this case, I'd randomize 1 and 2, or 0 and 1. Doesn't matter. I need 50-50 randomization between these two locations. If I decide to go up here, I visit that, then I do this. And actually, the first thing I do is I mark this visited, and I put this cell on the stack. So on the stack now, we'll put 0, 0, which is this cell. And let's say I visit up here. I break the wall between them. I mark this visited, and I put this on the stack. So now 0, 1 is on the stack. I randomize between what I can do. I can't go here because it's visited. I can't go here because it's out of bounds. Can't go here and here. I break down this wall. I actually physically do it by changing the south wall of this cell. Mark it visited. Put it on the stack. Okay, so my stack here, just draw it like this, stack. Let's just say, so I can, usually this will end up in a fairly long path all over the place before it can't go further. But I'm going to make exactly the randomization that will make it go super short. Let's say I visit here, I mark this visited. 2, 1 is now on the stack. I visit this one the next time, I break this wall. I have, this is 2, 0, 2, 0 on the stack. I break down this wall. Okay, now I'm at a point where west is out of bounds. No, sorry, south is out of bounds. West is visited, north is visited, east is visited. I can't go anywhere. So, wait, this was 2, 0, this was 1, 0. Okay, let's put it on the stack only if we can actually go from it. Fair enough. At this point, I pop the next cell off the stack and say this is now my current location. So my current location is no longer here. My current location is now here, and I check where I can go from there. I only have one, so I randomize 100% to here. I visit this. Let's say I visit this, this one again. Let's make it a ridiculously unlucky path that goes exactly to here now. I'm here, I can't go anywhere because everything around me is visited. I pop off the stack. I pop to here. This one is also only with visited cells around, so I can't do anything there. I pop off the stack. This one has possibilities, so I randomize between these possibilities. Here, go here, go here. You can see where this is going. We're ending up with this maze structure, and if we never go again to something visited, we never break the wall, another wall to any cell. So every single cell just has one entry and one exit, which means we end up with a completely enclosed maze. There will be no circles in this maze, and there will be no kind of wider hallways than one in this maze. So it'll be a very classic maze structure. What happens once we've gone all over the place, we filled the maze with every kind of, paths all over the place. That means we pop off the stack, can't go anywhere, pop off the stack, can't go anywhere, blah, 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 until we basically pop the last one off the stack and can't go anywhere, and we have an empty stack, and then we know we're done. So empty stack means we're done. Are there questions regarding this? Does this algorithm make sense? Okay. Again, I don't necessarily expect you to have random generated mazes, but it's fun. And if you set your maze up in this way, this is a fairly simple way to do it. If you set your maze up in different ways, fine. But I kind of wanted to do this just to show you this way that I think of mazes in this cell with south wall, west wall way. And this algorithm. Yes, question?
To enforce these curls and the dead ends, do you section up the maze?
To enforce these little curls,
yes.
You're going to get these curls into dead ends. The thing is, you're probably not going to get them as quickly as I do, but in the end, you're going to get some path that goes all over the place and then goes into a curl. After that, that path has kind of sectioned off a bunch of little places. So once you start backtracking, once you start popping off the stack and backtracking, this algorithm is going to end up with a lot of little curls. But you could section it off, yes. You could say, like, I'm going to only work in a part of the maze and just have variables that say I'm only going to go up to 3 and 3 in x and y, or x and z, until I've gotten a certain amount of cells visited. Then I'm going to make that restraint different. Because if you kind of finish it and have it sectioned off, then you need to find a nice place to start over again, and then maybe you don't have the same type of maze structure. But again, the fact that this is no circles, that's just a nice fact about this. That doesn't mean that your mazes have to be that way. I can add though that it's so much simpler for me to grade when there are no circles. If I want to actually get to the end of a maze and see what happens at the end of a maze, if you have circles in the maze, I can't do the kind of follow the left wall algorithm to actually get to the end. It's a very quick algorithm to get to the end of a maze, just follow always the left wall. As soon as you have a circle in it, something like this, that's broken. So no pressure, but it's also a nice thing to keep in mind, not the fact whether you have circles or not. Make sure that there's some level in your assignment that is a nice quick showcase to me of what's happening in your assignment. If I have to play your assignment for 15-20 minutes just to get to the cool part, odds are I won't see your cool part. But yeah, other than that, yeah, regarding this algorithm, yes, one more thing. Often we'd like to kind of use this algorithm as well to make a decision on where kind of the end of the maze is, or the beginning. In some cases you'd like the end to just be, I exit the maze. Then you can start this algorithm at the end and just say, I'm going to open one wall here, and this is, I found my way out of the maze. And then you can go all over the place and finish this algorithm. The question is, where would you want the other end to be? Would you want it to be the first place where you had to backtrack? That's very likely to be a long path. But in the case that we have here, it can also be a ridiculously short path. So, you found your way out here and you wasted the rest of your maze. Another way would be to say every time I backtrack, I'm going to check the size of my stack. And if it's longer than the last time I checked, I'm going to say this is my new end cell. And that means whenever you have to backtrack, you have a potential other end. And the other end that will have the biggest stack will also have the biggest path from the beginning to there, like the biggest correct path. So that way you can get the biggest correct path and say my end versus beginning should be the two ends of the biggest correct path in the entire maze. So that's one way of doing it, just checking the stack size. Or you can actually just analyze your maze afterwards. It doesn't take that long. You can make the maze, and then you can just kind of take different paths and kind of analyze paths through it and say, I'm going to just pick the longest path that I have in this maze and make that be my beginning and end. I think the simplest way, though, is the stack size one. Then you just have the longest path from whatever you chose as the beginning or end to whatever else can be a beginning or end. More questions regarding this assignment in general? Since we're like 1 week away from handing it in now, is there something you feel that you'd like to know better, or does this explain more or less the idea of what we're going to do? Except that it has to be displayed in 3D. It's a nice simplification as well to know that, the gameplay that we're doing in the collision detection, it's still just in 2 dimensions. We're not really doing physics in 3D yet. We're not doing anything in 3D except we're displaying our environment in 3D. So we're displaying 3-dimensional objects. If you want to, obviously, make sloped paths and do all kinds of stuff and actually do collision in 3D, but chances are none of you will have time to go that far for this assignment. So most of you will probably just be looking at, a 2-dimensional game in a 3-dimensional view. And that's fine. And it kind of simplifies it for you to realize that you can just say, okay, I have X, Y, and Z positions all over the place. But Y is just kind of the height of my head, and it's equal all the time, so I can just take Y out of it. And I'm just working in 2 dimensions, except those dimensions are the X and Z dimensions rather than the X and Y dimensions. Other than that, it's 2D physics, 2D game, sliding along 2D lines. You don't have to think of these as 3-dimensional walls. It's just 2-dimensional lines that you're walking into and sliding along. There, I answered my own question. Do any of you have questions? When can we get out of here? It's a good question. How about now? Have a nice weekend.